So we'll give you an overview of work package 5. So work package 5 is about ensemble runs and data assimilation using what is called statistical data assimilation techniques. And the goal is to go at large scales. We have two target scientific challenges, the Meteo with the EoCoE code and the water one with PowerFlow CLM, partners or CA in RIA, ULICH and PSNC. There is some hiring that has been done in the context. So we have one PhD student, Sebastian Friedman, that is here at INRIA, and two engineers at PSNC, so Bartek Pogodzinski and Anas Sekula. We're working together, so things are progressing, and we already did a face-to-face meeting in ULICH in June, so it was quite productive with the two scientific challenges. It's a small work package, so I think it's going to be a short presentation as well, compared to the other work packages. What is data assimilation and statistical data assimilation? You have two categories of data assimilations, techniques, some that just use one simulations, and some that use, let's say, a sample of simulation. The idea is that you have your simulations, and you have observations that you got from other means. Maybe you measure some temperatures. If you think about weather, you have weather temperatures records on the planet, and you have a simulation of the planet. And you want to basically take into account this observation into these simulations, so they both fit well together, okay? So that's the goal of data assimilation. So how you do that? The statistical data assimilation is using, there is a need to do that to compute some covariances. And so one way to do these covariances is not to run one simulation, to route many. So you have samples, and based on that, you can have an estimation of these covariance matrix, okay? So you have your simulation, that's every single blue points, that can be large parallel implication simulations that you make. So you have several ones. That's called members. So you have an ensemble run, and inside you have members. So you have n members. You progress in time, and at some point you have observations. So what you do from this sample, you get covariance. You compute the covariance matrix on the different states given by the different simulations. Then there is some math to do some minimization on variance between the simulation and the observation data. So you mix all things together to find an optimal point, hopefully. And then this give you, let's say, seed to give new starting points to the different seeds. So you readjust the states of the different members for the next steps. Okay. Here you may have some different variations. There is different things. Or you have the 3D VAR, you have the 4D VARs, you have particle-based simulations. They can do things a little bit differently, but that's the main idea. And then you progress in time. Okay. And this is challenging because you need a large number of members if you want your statistical sample to be significant, and every single members, as we're targeting large applications, use a lot of cores. So that makes a really, really big application, even if it's kind of embarrassingly parallel. So here are the current states of what has been done in data assimilation regarding EoCoE and PowerFlow. So EoCoE has already some very large runs with 4,000 members and using 2,062,000 cores. I think it was on ULICH machine. And PowerFlow CLM is using a data assimilation framework that is called PDAF. And they are more modest with 32 members and 3,000 processors with 75% efficiency. So there's two issues with this, is that when they do that, they just have a huge monolithic MPI code, and inside they use the MPI communicators to isolate the different instances of their members, and they gather the data, they do the data assimilation stuff, and it's very synchronous. So in terms of efficiency, that may not be optimal, even if they get a good efficiency. 75 is not that bad. And the other issue is fault tolerance. So if something gets wrong in one of the members, everything crashes. Okay. Of course, you can do some fault-tolerant stuff, but it's not that easy. Okay, and so what we are, one of the main goals of Work Package 5 is to try to have to explore the potential of a different approach, a more flexible one, based on a tool that has been developed at INRIA that is called Melissa for sensibility analysis, that we are adapting to the data assimilation context. So Melissa is different in the sense that every single member is basically submitted to the batch killer as a standalone MPI simulation. So you don't aggregate all the simulation, all the members in one big MPI job. Okay, so every blue box here is a different simulation with different input parameters. You have the different members. And then we have a Melissa, what we call the Melissa server, that is another MPI code, but also independent. And we have a client server-like dynamic connection. So when the simulation starts, it directly connects to the server. And so they're going to send the data through the server. The server will take care of the data assimilation logic, so compute the covariance matrix. And compute basically the new initial states for the other members, and you have to send back this information to the simulation so you can progress on time. Okay, and so we expect through this kind of framework that things are going to be easier to handle failures and easier to hopefully gain on the efficiency side. So it's probably easier to basically, if we can get some a little bit of flexibility to extract more asynchronism, to overlap the execution of the simulations, the simulation and the parallel server. Okay, so where are we? The project is starting, but we have a first Melissa, let's call it the Melissa data assimilation prototype using PDAF for implementing the data assimilation logic. So PDAF is one standard that is using this MPI approach, but the core kernels, we can reuse them, and that's what we do here. So basically, PDAF is there. Oops, sorry. PDAF is in the black box here. We put PDAF there for that part. For the moment, we don't have a real large-scale simulations. We use the PDAF example. They are very simple, but it's for validation. We adapted the fault tolerance, the Melissa fault tolerance, to the specificity of the data assimilation constraints. So this is on the working on the way, but it's the initial tests show that it's working. We did with the PSNC, we did some bonus development. So we supported, we developed some Jupyter notebooks, so the user can easily control the execution of all this framework from simple notebooks, and it works well. This is nice. And we have some early PDI support on the simulation side. Basically, we wrote an initial PDI plugin for Melissa. So now if, for example, we switch to Parflow and there is the PDI, Parflow has been reworked to support PDI. Normally, we shouldn't need to do anything on the Parflow code to be able to use it in the Melissa context. Okay. And next steps is to move forward. So use Parflow CLM instead of the toy example that are present in PDAF. Do work on the automatic load balancing strategies. There is some restart issues. I'm not going to go into the details here. Find some ways to improve parallelization efficiency by looking at how we could better overlap the computations of the data assimilation process itself and the different members. There is different approach we have in mind. We still need to experiment them. One is that Melissa has an engine to compute statistics iteratively, and that may help to basically compute the covariance matrix without having to assemble first all the different states of the different members, but to do this progressively, and so better overlap the computation of the covariance matrix with the progress of the different members. And we want to go even further in the explorations on how we could, let's say, introduce more flex in the process to gain more asynchronism and then improve efficiency. And then we also have to work on ESIAS. ESIAS use the different data assimilation processes, the particle filter. That seems, from what we understand, more flexible than the Kalman filter used currently in the Parflow code than we have, but this is still things that we need to explore. So that's from what I would say a scientific point of view. Then we have some 3 deliverables, and we're on track. So because just the first deliverable is due at m+18, so we still have time. And this is the initial specification of the architecture, so things were validated correctly. And then we have to move to the easiest and powerful applications, and up to be able to run some very large tests. And I'm done. So if you have questions related to work package 5. Thank you.